Hello there. In this part of the course, we are going to discuss the relationship between statistics and probability. The term statistics is the sample equivalent of characteristics for a population dataset. Say, if we somehow manage to record the eye color of everybody in the entire world and 65% are brown, that is a characteristic of the human population. However, if we make the plausible and much more reasonable choice of looking at maybe 1,000 people, then if 60% of them are brown-eyed, that is a statistic. After this brief introduction, you probably realized that the field of statistics focuses predominantly on samples and incomplete data. Doing so brings some uncertainty to any of the results we reach. This uncertainty is what leads us to rely on some of the most important concepts of probability, like expected values or prediction intervals. Fascinating. In a way, probability lays the groundwork for statistics because it defines terms like mean, variance, or expected value. Statistics tries to analyze numeric and categorical data and see how well it resembles any of the probability distributions we already learned about. Furthermore, since we are mostly dealing with experimental data, statistics introduces many useful concepts based on probability theory. One which we will shortly explore is that of confidence intervals. A confidence interval, or CI, uses sample data to define a range with an associated degree of certainty. These degrees of certainty are usually 90%, 95%, or 99% and express the likelihood of the population mean being within that interval. A more hand-wavy explanation of confidence intervals is that they simply approximate some margins for the mean of the entire population based on a small sample. To calculate these confidence intervals, we must know what mean, variance, and standard deviation are. Thus, having a good understanding of probability is crucial. If you follow through with our program, you will learn much more about them. But let's get the gist of that real quick. Imagine you are on a trip to see your favorite soccer team in North London. You want to know how much money you should carry with you when you go for a meal before the game. So you gather some data. More precisely, you examine the average prices for a main course meal in North London by going through the menus of some 10 restaurants and pubs through Yelp. The mean of the data you gathered is £22.50. So you expect a meal to cost approximately that much. As we have stated throughout the course, when we are uncertain of some outcome, we construct intervals. The mean of our data is £22.50, so we build our interval around it. We know that prices in the region are normally distributed, so the data is symmetric with respect to the mean. Therefore, our interval should be equally far away from the mean in either direction. Without going into too much detail, our confidence interval should span between £20 and £25. This indicates that we are 95% certain the average meal in North London costs somewhere between £20 and £25. So that is how much we intend to have. Okay, another important aspect of statistics is hypothesis testing. We only mentioned it earlier without really explaining what purpose it serves or how we use it. Loosely, a hypothesis is an idea that can be tested. Stepping on the previous example, I may want to test if the average price of a meal in North London is lower than 30 quid. To do so, I would place the value on the graph and see where it fits. If a small part of the data lies to its right, then the statement is probably correct. To determine how small this part is, we need to know several attributes of the data. Mathematically, the three crucial requirements for conducting successful hypothesis testing are knowing the mean, variance, and type of the distribution. With the help of these three and some formulas, we can validate similar statements, again to a specific degree of certainty. All right, in the field of statistics, we are often provided some sample data without explicitly being told what type of distribution it follows. We usually determine that on our own, based on the shape of the curve and certain characteristics of the data. Just like when we are buying a new sweater, we might think one of them is a good match, but we can't be sure until we test it. Sometimes we find exactly what we're looking for, but other times we go for the closest match that we've got. The same logic is often applied in statistics. When determining the distribution, The way it works is the following. For starters, any distribution we try on predicts a value for all points within our dataset. This is what the distribution anticipates the actual data point to be, so it is essentially a type of anticipated average value. So the more distributions you know, the easier it will be for you to determine which one you're dealing with for a certain problem. Fantastic. After finding the distribution we are dealing with, we like to create different models, such as regressions. Since the mathematics behind regressions is complex and computationally expensive, we use computer software to find the appropriate values. We call this entire process mathematical modeling. It is essentially an extension of statistics that data scientists deal with. In fact, what statisticians and mathematicians call mathematical modeling is what data scientists often refer to as supervised machine learning. In essence, data science serves as a natural expansion of statistics in the very same way statistics is the natural expansion of probability. In the next video, we are going to focus on the relationship between probability and data science. Thanks for watching.